over triple integrals. Okay. So triple integrals in spherical coordinates. All right. Now we went over cylindrical, and hopefully cylindrical wasn't that bad. It's just polar coordinates with another variable. Spherical coordinates can be a little painful. I'm not going to lie. So it's in terms of two types of angles. So it's in terms of rho, theta, and phi. Okay. Now, this is actually a very interesting way of using cylindrical coordinates because you're going to get a circle no matter what, or a type of circle. So how this works is given the XYZ plane. So I have a vector going from the center, let's say, to here. Here's my point, rho, theta, and phi. So this length here represents rho. This angle from the z-axis to here is the angle phi. And then theta goes from the x-axis and how much I'm rotating all the way around. So if I project this down to here, for instance, I'm rotating this all the way around depending how I want. So I actually get a circle. So rho has to be greater than 0 to be true. And we have a condition on phi, our new angle here, is always between 0 and pi. Now, the reason why, is going from the x-axis, and if we go all the way down to the other x-axis, or sorry, the z-axis, it has to be with pi, right? It doesn't go any bigger than that. That gives you the half circle you want, and theta rotates it to get the entire circle or the sphere itself. So you get something like this happening. Now, we'll always convert to spherical coordinates whenever we're given some solid that's centered at the origin. That's the key thing. It's centered at the origin or centered at a point itself. Okay. So, for example, this is centered at the origin. We're automatically going to go into spherical coordinates. Centered at the origin, centered at the origin. Now, spherical coordinates can be pretty tricky because the way to convert is much, much more difficult to deal with. However, you can see the remnants of the polar coordinates. So to convert from XYZ to rho, theta, and phi, we have these conversions right here. So as you can see, we see out the cosine of it from the polar. So this represents right here is our radius. So that's how we get the radius from here to here. So this radius is in terms of just phi sine, I said rho sine theta. It's confusing. Rho sine phi. So how do I get this radius right there? So it's an interesting way to get that. Okay. Now, before we actually get into integration with respect to spherical coordinates, so let's just see how we can convert some stuff. So you can see how to find each individual angle and how we're going to do it for these type of questions. So all we're going to do is convert this point to our new coordinates. So our new coordinates look like that. Okay. So the easiest one to do is always going to be rho. That's just going to be the magnitude, basically, of all the points, right? So 0 squared plus this squared plus that squared. So this ends up being 0. This is 4 times 3 is 12. Plus 4 gives me 16. So rho is going to be 4. Okay. Now from there, you actually want to go backwards. So from there, we're actually going to go using z now. So using z, we have 2 equals rho times cosine of phi. So we're going to have 4 is equal to, sorry, 4. 2 is equal to 4 cosine phi. And we're just going to solve for that. So divide it over. So therefore, the only time cosine is equal to 1/2 is at 1/3. So we know phi must be equal pi over 3. And then from there, you get to choose which one you want to deal with. And I don't want to deal with the square root stuff, so I'm just going to put 0 instead. So I know 0 must equal 4 sine phi cosine theta. And then phi, we know it's pi over 3. So sine of pi over 3. What is that? So 3, 2, 1. 3, 2, 1 is about radical 3 over 2. Yeah. And it really doesn't matter because this is going to be equal to 0. So if I just divide us all over, it just gives me 0. So the question is, when is cosine equal to 0? Pi over 2. So 1 point this is going to be, because there's multiple, because theta can vary. Would be this. Now remember, what I mean by 1 point is because cosine equals 0 at multiple points, right? So this could technically be 2 pi over 3 as well. So that's another alternative point we can have. Same thing for cosine. Right? Well, actually, that has to be fixed because this has to be bounded between 0 and pi. So that's the only point there. Right? So multiple variations of these kind of stuff. All right, so now that we have that going on, let's try to figure out how this integration is going to look like. All right, so just like we did for polar, right? We going over a somewhat of a rectangle, but this time this rectangle is curvature, so we call it a wedge. So this wedge kind of looks like this. It's a pretty interesting, nifty little concept how this works. You know, it's very complicated, but it's very surprisingly interesting how it works. So think of a rectangle. Yeah. But now I'm just bending it around. So kind of now looks like this. Like that. So that's what we call a spherical wedge. Okay. So that's the spot where we're going to be finding the area or the volume of it, and then just rotating or taking the limit, you know, as this goes infinity, and that's going to be our type of way we're going to do our triple integration. Now again, this is the interesting part when it comes to the angles themselves. Okay, so when it comes to theta, we're going to say beta minus alpha must be less than or equal to 2 pi. So, right, can it be anything bigger than that? Okay. And alpha must be strictly greater than 0 when we rotate this all the way around. So, and again, remember that represents the angle itself. So from here to here is where we get these conditions have to be. So the rotation going around the x-axis has to be between basically, 2 pi. It can't be any higher than 2 pi itself. Okay. Now, the nice thing about spherical coordinates is rho is the only thing in terms of a different variable. The angles will always be with respect to angles, which is nice. So rho can be in terms of both the angles, which could be a pain, but the good thing is automatically after that it's going to be probably between 0 and pi, 0 to pi, or pi over 2 to negative pi over 2, things like that. Now, how do we go from xy to spherical integration? Well, it's the same thing when we came to polar. So polar, it was r multiplied by an r, and same thing applies here. We're multiplied by a phi times r, or in other words, a phi squared cosine there. And that's the key thing. It's rho squared sine phi. So, and in terms of that, again, you could change the balance between theta and phi, but rho always comes first, or the p, if you want to call it as p. That would get confused. Okay. Again, where this is our spiritual wedge. So we're rotating that little part all the way around. Okay. Now I say this laughingly, right? Say easy first, because this may look like a pain, right? So let's find the triple integral of this ball, where B, so this region B, is the ball of x squared plus y squared plus c squared equals 1. Okay. Now, I'm going to attempt to actually draw this, and it's actually not that bad to draw this figure because it's just a sphere. So this is what's happening. So hopefully this makes a little bit more sense now going forward when we do these equations. So I have a sphere centered at the origin with radius 1. Okay. Now, rho is the radius from here to there, for example. That's what rho represents. So as you can see, rho has to be between 0 and 1. And that makes sense, right? We just plug it in. So we know by our definition that this is equal to rho squared, or the square root of it, right? That's the algebra version. This is geometrical approach of it. Okay. And I know that in order to get down to here, I have to rotate this from one end to the other end. Well, I rotate that half the portion, right? Or just pi. If this is 0 all the way to pi. So therefore, phi has to go from 0 to pi. And then lastly, how much am I rotating from x all the way around? So now I rotate this way and this way. So that gives me like the half circle there. And then I'm rotating this all the way around a complete circle. That's theta. And there we go. So when it comes to these examples, that's exactly what you kind of want to do is figure out, okay, what am I rotating? How far am I rotating? And vice versa. Now, sometimes, unfortunately, phi is not as simple as theta, and we have to convert, plug it in and stuff like that. But most of the time, as you see a sphere, goes straight into that kind of concept. So therefore, now I can rewrite this, and I know that this part right here is going to be phi squared. This becomes the integral of 0 to pi, 0 to 2 pi, and 0 to 1, our new equation of e to the phi squared raised to the 3/2 power times, and don't forget to plug this in. Like that. So if I clean this up a little bit, this ends up being just phi to the third, right? Now, quick little note. I'm going to be using this little note a little bit in this section and probably going forward as well. We had a theorem that stated you could break up this integral as long as there's multiplication, right? In each individual parts. So for example, if I rearrange this, this becomes, again, right, cancel, phi third. So what I mean by that is I could do each individual integral with respect to its own individual variable. So for example, if I just use the phi's, I'll have 0 to 1. Like that. Okay. Now that's just easier to see the integration because it's so much stuff. You don't have to do this. I will do this because I will always get confused of this kind of stuff. For me, it's just too many letters and too many Greek letters going everywhere. So most of the time, I'm just going to break it up just like that. And again, you can do this if everything's being multiplied individually, right? So you have this together, that together, and then just the one with respect to the theta. And you get the same result if you just don't do it this way. But there was a theorem we could do this. So, we could just do the individual and we just multiply the results at the very end. Okay. So this makes it a lot easier to look at, right? Because you just take the integral of each individual step individually. So for example, here, use substitution. So we just divide by 3 and call it a day. So this says I'm being 1/3 the integral of just e to the u, which is just itself, right? So this ends up being 1/3 integrated from 1 to 0. So it becomes e to the phi to the third integrated from 1 to 0 times integral of this just gives you theta. So times theta, evaluate at 2 pi and 0, and times this. So integral of sine gives you negative cosine. So times negative cosine, evaluate at 0 and pi. So plug in 1, you just get e Plug in 0, you get 1. So times, plug in, well, it just ends up 0, so you just get 2 pi here. And on this side, you plug in pi, you get -1. So -1 times -1 gives you +1. Plug in 0, you get 1, -1, so you get that. So I don't know if it's easier for me instead of having to do all this stuff. And you could do that for any triple integration. I just do it more here because it's just easier to look at. Okay, so this gives me 2. So 2 times 2 pi times this subtraction. So you could leave it like that. So I just left it like that. So 4 pi over 3 minus the subtraction. Or you could just give me the actual answer. I was just too lazy to get plugged in a calculator. So I say it's easy because this integral wasn't that bad to do so, right? So now let's do a little harder one. All right, so find the volume of the solid that lies within the cone and below the sphere. Okay, so what this is saying is I actually want this stuff right here. So here's my cone. And within the sphere. So I want kind of like this portion right here, where this is cutting right there. So as you can tell, this is like the lower half. And then this is the upper half we want from the sphere. So pretty much this in color. So this is the one picture of it. And this is the top version of it. Okay. Now, if you want to attempt to draw this, it's not that bad to actually draw this time. So let me show you how it will work. So it looks something similar to this. So we have the V shape from here, right, going around, and then we have the upper part. So now if we put coordinates to it, here's X, here's Y, and this is Z going up there. Okay. So phi will go from here to some point on the surface that represents our radius. Okay. And remember, sorry, rho. And then phi goes from the z-axis and how much I'm making it angle from here down to when it touches the very tip. So it's this angle there. This represents phi. And theta is how much I'm rotating until I get back to that point. So it kind of gives it a precursor of what's going to happen. So now you can tell phi is not going to be from 0 to pi because I don't go all the way around completely down here, right? So I got to figure out what angle does it stop at right there to make this true. Now for that, we're going to have to actually do the algebra instead of using the geometrical approach itself. Okay. So first, let's figure out what each one's going to represent. So using this one right here, so we know that rho squared is going to equal to rho cosine phi. So dividing both sides, we get phi is equal to cosine that one. So this time around, rho is in terms of another variable. So we have from 0 to cosine phi. Okay. All right, so to find what this one's going to be, because we need both of them. And you can probably tell theta is going to be from 0 to pi, but we'll get there once we get there. Now we use this one right here. Okay, so this one represents, this one says phi cosine, rho cosine phi is equal to the square root of x squared, which is going to be looking like that. Okay. So I'm going to quickly just skip a step here. So if I multiply this, right, everything's being squared, right? Everything's being squared. And if I factor out a p and sine squared from each one, I get cosine squared plus sine squared, and that equals 1. So this ends up being simplified down to this, which just equals that. And if I just divide out the p's, so we know cosine phi must equal sine of phi. And then now you got to figure out when is cosine equal to sine, and that's always only at pi over 4. And again, remember, because it has to be bounded between 0 and pi, it can't go any higher than that. So you only get one solution. So it goes from 0 to pi over 4, where it hits this boundary right here. And again, cosine we know, or sorry, theta goes from 0 to 2 pi, right? Just rotate it all the way around the entire circle. All right, so now we have their triple integral. Now the question is, what am I integrating? That's a good question. It's actually just 1 times our conversion, because we didn't really give us an actual curvature to go by, so it's just going to be 1 times that. That's the reason why it's a little harder. All right, so this one I won't break up so you can see that, how the process is. So this is just going to be the third over 3. Evaluate at 0 and cosine. So plug in 0 goes away, so we just get cosine cubed. I'll put the 1/3 on the outside. Theta. The nice thing is it's theta, so it just becomes a theta. Plug it in. So we just get 2 pi over 3 times integral from 0 to pi over 4 of this mess here. But nothing to use substitution can quickly do it, right? So let u equal cosine. So therefore du is negative sign. So just pop a negative on the outside. So it's going to be negative 2 pi over 3 times cosine to the 4th power over 4. Evaluate it at 0 and pi over 4. Right, so just in case you're not sure, right? Gives me that. So what does this give me? So cosine of pi over 4 is radical 2 over 2 minus cosine is, to the 4th power. Oh boy, to the 4th power. I'll pop this out here and make it 12. Make it easier for myself. And then cosine 0 just 1. So that's kind of nice. Gives me that. Okay, so I simplify this as much as I approximately can. And I got roughly, approximate 0.39. Right, so first to the 4th power, minusing 1, and then negative, because it's going to be a negative here. And negative makes a positive, so you get actually a positive, which is nice. All right, let's try one more. All right, let's find the triple integral of y squared dv. So the volume of this solid, where the solid being generated is the hemisphere, which is even nicer, right? So it's the first hemisphere that's greater than or less than 9 and greater than 0. So here's our plane, y equals 0. So it's just the first hemisphere, which is nice. So it's just this rotation. So everything positive, right? So half the area of the sphere, basically. So you can kind of already tell what's going to happen when I rotate this down here and then rotate this all the way around, right? That's going to be here to here, rotates all the way around, and here to here. But, algebraically, you plug it in. So this is going to be, this implies less than 3. Okay. All right, so just like I talked about, so then again, theta. Okay, so theta going all the way around the unit circle. Right there. Now phi. So if phi is the angle between the x-axis and P itself, right? So phi would go from here down flat. So that goes from 0 to pi over 2, just like the last one, or half of it, right? All right, so, and then y squared is going to look like this horrible mess. So we're going to have this triple integral. Okay, so last one is going to be this one. So 0 to pi over 2, 0 to 2 pi, and then from 0 to 3 of all of this. Times our conversion. All right. Putting everything together gives us approximately this. And this time I am going to split it up because it just looks horrible to begin with. So we'll just do the easy one first. Yeah. All right. We'll talk about this one in a little bit. Let's just do the first two. So hopefully this is a straight, oh, it's the fourth power. Straight integration here. So phi to the fifth over 5 evaluated at 0 and 3. Okay. This one we use the same rule we've done before, right? The integral of sine to the second power is just going to be equal to theta over 2 minus sine of 2 theta over 4. Same conversion we've been doing. This one, however, is the painful one. So I know it's been a while since integration. So just in case you guys forgot, when you have anything higher than 2, well, this is the same way you would do it here anyways. You want to split it up. And we know that sine squared, another way to write that is 1 minus cosine squared. And then if I distribute, you get that. So this integral ends up being 2 integrations. So just integrating this and integrating that individually. So we just get the integral of this. This is straightforward, right? It's just NZ minus cosine. This one, you have to do a u substitution. So let u equal cosine. So therefore, the derivative is going to be a negative sign. So this ends up being the integral of u squared. So negative u to the third over 3. There's that minus on the outside. And then minus minus makes it positive. So we just get that. So it's going to be plus cosine to the third over 3. Evaluate 0, pi over 2. Whew, all that, huh? Okay, now that we have all this done, let's evaluate. So plug it in 3, 0 goes away, so there's nothing going to happen there. So this is going to be 3 to the 5th over 5 times. Plug in 2, well, plug in 0. Sine of 0 is 0, so all this is gone when it comes to 0. So plug in 2 pi. What do we get? So plug in 2 pi, we get just pi minus, well, sine of 4 pi still gives you 0, so just ends up being pi. Times on this end, what happens? So if I plug in cosine of pi over 2, what does this end up giving me? Oh, wait, did this really raise radical 2 over 2? No, actually, what am I doing? Cosine of pi over 2 is 0. So this is 0, and that's 0. So all that's gone. All right. Plug in 0. So we have 0 minus. Plug in 0, I get 1. Plug in 0, I get 1. I get that. Okay, so this ends up being negative 2/3, but negative makes it positive. So I get 3 to the 5th over 5. Just put the pi in there. Times positive 2/3. Well, I guess we can simplify this a little bit. It's a 4 now. So 3 to the 4th times 2. I get 162 pi over 5. And that's